I'm Heikyu Park from Georgia Tech. I'm very excited to present Bluff, a visualization tool to interactively decipher adversarial attacks on deep neural networks. Deep learning is now commonly used in many domains. For example, in the medical field, deep learning models can estimate the treatment effects on patients. On the road, we can see self-driving cars using computer vision technologies. However, deep learning models are vulnerable to adversarial attacks. An adversarial attack applies carefully crafted perturbations on data inputs and fools a model into making incorrect predictions. Adversarial attacks jeopardize many deep learning-based technologies, especially in security and safety-critical applications, such as data-driven healthcare and self-driving cars. Due to the threats of the adversarial attacks, people cannot confidently use deep learning models. To overcome the vulnerability of deep learning models, we need to understand how the adversarial attacks permeate the model's internals. Also, for a better understanding about adversarial attacks, it would be worthwhile to examine if and how an attack strength changes how the model produces incorrect predictions. For example, it would be useful to know if a stronger attack exploits the same neurons as a weaker attack does, or if those sets are completely different. We present Bluff, an interactive visualization tool for discovering and interpreting how adversarial attacks mislead DNN into making incorrect predictions. Our main idea is to visualize activation pathways within a DNN traversed by the signals of input data. For given input data, an activation pathways consist of neurons that are highly activated and the most influential paths. Activation pathways represent what features are detected and how those features are related to contribute to the final prediction. To understand how the attacks manipulate the neurons and the paths inside the models, Bluff visualizes the activation pathways of both benign inputs and attacked inputs. That is, Bluff finds and visualizes the most activated pathways given benign and attacked input data. Bluff also visualizes the most inhibited paths by the attack to uncover where the attack is blocking the signals to the benign path. Also, Bluff visualizes the most excited paths by the attack to uncover where the attack stimulates to induce the activation pathways going towards wrong directions. The Bluff interface tightly integrates three coordinate views. It consists of control sidebar, graph summary view, and detail view. Here, a user inspects why a deep learning model misclassifies adversarial giant peta images crafted by the projected gradient descent attack as armadillo. In the main graph summary view, we visualize the activation pathways of benign and attacked input data. Here, each vertex represents a neuron. When hovering over a neuron, Bluff shows the detailed information of the neuron. The detailed view for a neuron shows a feature visualization and example data that visualize what feature the neuron is detecting. For example, for giant panda images, this neuron looks for face of animals that have white furs and dark eyes. Feature visualization is a synthesized image that maximizes the corresponding neuron's activation. Dataset examples are patches of images from the training data that highly activate the corresponding neurons. We also show how the neuron's median activation will change according to different attack strengths. Here in the graph summary view, the neurons are represented with different colors based on their roles. The green nodes are the most important neurons only for the original class giant panda, which means they are highly activated by benign giant panda images. The blue nodes are important neurons only for the target class armadillo. The orange nodes are the most important neurons for both original and target classes, giant panda and armadillo. The red nodes are the neurons that are highly activated by only successfully attacked images. These neurons are exploited by the attack to induce the incorrect prediction. By exploring the activation pathways, PGD successfully perturbed pixels to induce the brown bird features, an appearance more likely shared by an armadillo than a panda. Both armadillo and brown birds have small, roundish, and brown bodies. The brown bird neuron then contributes to the armadillo misclassification by activating more features such as scales, bumps, and mesh. By using the options in the control sidebar, users can interactively filter the neurons and connections to visualize. For example, they can select to visualize R graph
All right. Welcome to our session on decision making and reasoning. My name is Jordan Crouser. I'm an assistant professor at Smith College, and I'll be your session chair for today. So our first paper is Cava, a visual analytics system for exploratory columnar data augmentation using knowledge graphs by Dylan Cashman and several colleagues. And Dylan will be giving our first talk this morning.
Hi, I'm Dylan Cashman from Novartis, and I'm presenting work for my PhD at Tufts University called Cava, a visual analytics system for exploratory columnar data augmentation using knowledge graphs. So I'm going to describe to you in 30 seconds what all visual analytics systems do. So we all know that we want the user to get insights from data, but the raw data itself might not be the appropriate format for the user. So maybe we render some visualizations using that data and show those to the user. Maybe the data is complex, so we have to use analytics to find better representations that we either feed directly to the user or visualize themselves. And this workflow here describes a lot of visual analytics systems. A lot of visual analytics research has to do with refining these arrows or maybe turning them around or refining one particular aspect of this loop here. Today, I'm going to talk about a system that focuses just on the left side here, on the data in particular. So our insight here is that that data isn't static. This data is born from context, actually. There's a lot of information about the data, like where it came from, what it's connected to, maybe, that can actually be important for our downstream tasks. When you think of data that way in this loop, it becomes useful to actually have the user decide which parts of that context they want to bring in that will then affect their downstream tasks. And this brought us to make Cava, or Columnar Data Augmentation through Visual Analytics. So Cava is a visual analytics tool for augmenting a tabular data set with new columns from knowledge graphs. And there's really two contributions, and they sort of go in opposite directions. So first, we present a design study of applying visual analytics to columnar data augmentation as if it were its own domain. But then we turn it around and we look at how columnar data augmentation can actually just be added as part of the visual analytics workflow. And we validate that by showing how downstream tasks can be improved by including this as a step. So I'm going to start treating this as a design study. We're going to look at the data we have, the tasks the user wants to accomplish, and I'll speak briefly about knowledge graphs, which are external data source. Then I'm going to describe the Cava system, and then I'll talk about our evaluation, which was a user study and some usage scenarios. So we assume that the data the user comes with is a tabular data set. So here's a typical example. This is a sales data set for some company. So there's 4 columns, and then maybe our target variable, the number of sales in this year. And maybe we want to understand how we can improve the sales or how we can predict the sales. And right now we don't actually have a lot of data to do that, but we have this very rich column, the country. There's a lot of context in there that might help explain why sales are what they are, but that context doesn't live in this data set. So as a user, I might want to discover data related to a given column as my first task, and then join through that data to specify complex attributes. To do that, I'm going to use a knowledge graph. So a knowledge graph is a graph-based information repository that stores entities and relationships as nodes and edges. So here we see Germany and Denmark are 2 different entities, 2 different nodes on the graph. And there's an edge between them that signifies that they share a border with one another. And knowledge graphs can capture one-to-one or one-to-many or many-to-many relationships. And they're often paired with an ontology to give semantic meaning to these links. They're being used more and more now because of how they can describe rich relationships and a very diverse set of relationships. They're used for search engines when you search a term and immediately some details pop up. They're also used in a lot of AI agents to answer questions. For Cava, we use Wikidata as the external data source, which has a lot of the same information as Wikipedia. So let's look at how we would accomplish those two tasks in Cava using a knowledge graph. So the first thing Cava does to discover data related to a given column is it takes the column of values and then maps each row of that column to a node on a knowledge graph, so these 4 nodes, and it wants to find attributes that are joinable for the entire data set. So what it does is it looks at all of the relationships in the neighborhood of each of those nodes, and then it merges the list of related attributes along each of those nodes and returns a list of the most common related attributes. And this sort of ranking is important because, just as an example, Germany in Wikidata has about 1,200 related attributes, whereas some smaller countries might only have 200 related attributes. So we want to try to find, in sort of a quick way, what are the attributes that are most prevalently found throughout our entire data set, throughout every value of that column. The second task is to join through that data to specify complex attributes. So in the same way, we start with a column, and then we map each row of that column to a node on the knowledge graph. And then each augmented datum is the result of a query over the knowledge graph in the neighborhood of that node. And so these queries can be really simple. So maybe we join on the area, and we're going to do that for each row of our data set, or maybe the population. But we can actually build really complex attributes just looking at this knowledge graph here. So we can join, for example, the average neighbor GDP. And you can see to build this, what we have to do is we have to actually go through intermediate nodes. We have to connect to Denmark, France, and Austria, among others, because those are the countries that share borders with Germany. Then we connect to their GDP. And then as we move back to actually construct this value that's going to be joined in our table, we actually have to specify aggregations, sometimes one at each step. So as an example here, once we get the GDPs, then we have to specify the average of those GDPs to fit into that one row. So you can see how we could construct this on a knowledge graph, but actually specifying that type of query can be fairly difficult for the user. So in Cava, we want to support these two tasks visually. So these two tasks, and we have some other tests in the paper as well as some other goals that I'm not going to talk about now for issues of scope, but these lead us to two design goals. So first, explore the set of potential attributes visually, give the user some indication about which attributes might be better for their analysis. And then the second goal is to provide visual examples for complex queries so that it's easy for them to understand the query they're building. So here's a screenshot of Cava. I'll go through it very quickly here, and then I'll show you some of the interactions. So in the top left, we see a list of the columns that are currently found in the data. And then at the bottom, there's an example of a few rows just to ground the user in what their data set looks like. And this updates as they add on new columns. Once the user selects a column that they want to join off of, they get a list of related attributes. This is related to task 1, like when we found GDP as related to the country. And we also provide some metadata. So the donut chart says what % of rows of the data set we believe we can join to. And then we also show some distribution of the data to give the user some preview of what they're actually going to join to their data set. When the user wants to discover new attributes, all they have to do is they click on a string-like column in their data set, and then it's going to just find a list and rank it by what it thinks is most relevant and send it back to them. Now, the user could choose to join any of those columns on, or if they want to select a more complicated join, they can join through intermittent values, and then the system will show them a preview of what their query will look like for one example in their table. So here we're joining on the state. We want to count the number of official languages of bordering states. I'm going to let it come around again. So when the user specifies they want to start with a count, it's going to show them an example on the knowledge graph for one row in their data. And this will update dynamically as they change these operations. So it makes it a little easier for them to build these complex queries. Okay, so our evaluation here, we have evaluations for each of the types of contributions. So the first one we're going to talk about is validating whether adding data augmentation to existing visual analytics workflows can improve downstream tasks. We have two usage scenarios that we talk about in the paper. So the first, we demonstrate how new insights can result from augmenting data. So we take a data set, we look at it in Tableau, then we add some new features and show the types of analysis that you can do using Cava. And then the second usage scenario, we show that a machine learning model that's trained in a data set, its accuracy can be dramatically improved by just a few rounds of analysis in Cava by adding a couple new columns. And then for the design study of applying VA to data augmentation as a domain, we have a usability study. We gave the user two tasks. First, join a set of attributes based on plain text prompts. So, they would see a prompt like that and be asked to join that data. And then also an open-ended task of joining a set of attributes that might help build a predictive model. We gave them a survey afterwards, and generally they found the system easy to use here, so higher is better. We also gave them TLX to find their cognitive load, and that was very low. So we found it was very easy to use our system to do these tasks. So in conclusion, Cava is a visual analytics application that helps users augment their data with additional columns found in knowledge graphs. Users can explore available attributes found near matching nodes on the graph. And to specify complex attributes, they can dynamically build queries with a visual interface. In two usage scenarios, we demonstrate how downstream visual analytics tasks can be improved by integrating columnar data augmentation. And in the user study, we show our technique is highly usable. And the code is available at the Tufts Vault GitHub. I want to mention I work at Novartis in the data science and AI group now, and we're hiring. We're looking for experts, PhD graduates, and interns in visual analytics and data science. We have some really cool data to work with and really cool usage scenarios. Like
John, will you give us a countdown before we go live?
Left there. And we're located in Boston, Basel, and Hyderabad. So please contact me
Dylan,
if you want to find out more.
Your audio.
And lastly, I want to thank all my collaborators at Tufts, Georgia Tech, Wisconsin, and San Francisco State University. Thanks a lot.
Dylan, thanks for a great talk. I've got a question from Thomas Davidson, who asks, when you talk about the system selecting and sorting the most relevant fields when you're providing the possible augmentation to users, how does the system decide what is most relevant?
Yeah, that's a really good question. As part of the requirements gathering for this, we interviewed designers of visual analytics systems to see what sorts of things they thought their users would want to know. And that was something that was brought up. Right now in Cava, it's pretty basic. It just tries to it basically sorts by the amount of rows it thinks are going to be joinable. So in the example, we saw maybe 100% of the countries had GDP. But in a lot of use cases, it's lower. It's like 50 or 60% for many of the potentially joinable columns. So that's what we sort by initially, but we also try to show that metadata, like the rough distribution, some example values. Those don't make it their way into the sorting, but we hope that that makes it easier for users to find the most relevant columns before they actually go through the expensive join operation.
Great. Well, thank you so much. I was wondering, really quickly, because we're almost out of time, could you just tell us a little bit about where you see this work going next?
Yeah, so I think actually the next step is to make this software much more usable. So right now it's all wrapped up in a system, but really this could be a service or an API, because I think it's a pretty universal value add in any visual analytics workflow. It should be easy to just integrate this as maybe a Python package, and so that you can let your users do some sort of data augmentation, add new columns initially at the very beginning. I'm also in the process of working on this at Novartis. We're looking at, with Wikidata, we looked at more generic data. Now we're looking at more domain-specific data and trying to understand what sorts of joints domain scientists and domain experts want to do.
Great. Well, thank you so much. Post your applause in the chat for Dylan.
Excellent.
Thanks so much for joining us today. Up next, we have an examination of grouping and spatial organization tasks for high-dimensional data exploration. This is work by John Wenskovitch and Chris North, and I believe John will be our presenter today. So if we could roll his video.
Hello. The title of the work that we are presenting here is an examination of grouping and spatial organization tasks for high-dimensional data exploration. That's certainly a mouthful, and so let me try to give you a bit of background about what it is that we're trying to do in the study that we're presenting here. So my PhD dissertation work was very focused on doing a deep dive into clustering algorithms and dimensionality reduction algorithms. In particular, how do we use both of them at the same time in the same visual interface? And so at VIS 3 years ago, I presented a paper where the focus was primarily on creating these visualizations. I also had a paper that would have been presented at IUI this year had COVID not happened, where we looked at the interaction space. And also, as part of my dissertation work, I developed a number of different implementations that looked at these different pipelines and looked at these different interaction techniques. But with all of this research already done, there was one big question that was still bothering us that was missing. And that question is, well, how are analysts actually thinking about these operations? If an analyst is approaching a completely unfamiliar data set, how are they going to go about organizing and structuring their space in the middle of a sense-making operation? How are they going to start grouping items? How are they going to start spatializing items? We started off with a pilot study with 2 participants just to work out some of the bugs in the study. In particular, one thing that we found was having floating point data really increased the cognitive load, and so we had to substitute all of our values for integer data. But eventually we got around to our full study, where we had 16 participants in total. And what we asked these 16 participants to do was to take a stack of 17 index cards, each of which represented an animal. Each index card had 5 different dimensions on it describing the animal, and we asked them to organize the space given the data that they had on hand. And in particular, we asked them to only try to use these grouping and spatial interactions, to only say, I am putting this animal in this group, or I am positioning this animal this location from this other animal, from this other group, and to use a think aloud process so that we could understand their actions. One other bit of the study is that we had both a labeled and an abstract data condition. And what I mean by this is that half of our participants got cards similar to the ones on the left, where they knew what the data represented. They knew that an animal was the killer whale. They knew that the dimensions that were describing this animal were furry, big, swims, fierce, and solitary. But the other half of the participants only got this abstract data. They only knew that this was card number 9, and that there were 5 dimensions A, B, C, D, and E, which had data normalized from 0 to 100, representing some purpose to the underlying data. And so what we were trying to find with this study were, well, a variety of research questions. In particular, they focused on 4 different broad areas. The first area was the participant analysis process. And so both when an analyst is starting to look at this unfamiliar data set, what are the first things that they do? What are these first actions that they're taking during their initial evaluation? And then after that, well, how do they have an overarching strategy throughout their sense-making session? How do they start transforming this completely unfamiliar data set into an organized space that is meaningful for them? The second area was what representations were they creating? And that goes back to we're focusing on these grouping and spatial interactions and structures. We wanted to know what kinds of grouping and spatial structures they were creating and how these individual dimensions from our high-dimensional data set were appearing in these organizational spaces. In addition to the representations themselves, we were also interested in how were the participants interacting with these representations? What kinds of grouping and spatial operations were they performing? Were they creating hierarchies of clusters? Were they creating and destroying clusters? Were they merging clusters? And then the final research area for us was this effect of domain knowledge, looking at the difference between our labeled data condition and our abstract data condition. What was the role that this external information played in our participants' analysis process when they had the labeled data? And also, we gave our participants in the abstract condition information about the animals at the very end of their analysis session, and we wanted to know how their layouts that they created would change whenever they were provided with this labeled information. So let me walk you through an example organizational strategy that one of our participants undertook. This was one of our participants in the labeled case, and so the participant had the names of the animals and their attributes. The very first thing that she did was she scanned through all of the index cards and looked at these different attributes and decided on size as a starting point for her analysis. Next, in part because of the space constraints on the table, she began binning the animals. And binning these animals weren't creating bins of equal size, it was just the best, most natural fit for her analysis process. Scanning through the attributes again, she next selected swims for an attribute to analyze. This time, instead of binning, swims was treated as continuous data. The bins were still maintained along the x-axis, but there was a more continuous spectrum along the y-axis for swims. At this point, the participant was beginning to start thinking about formal clusters in the data, originally creating these 3 clusters for animals that do swim, sort of swim, and don't swim, but then eventually breaking that swims cluster up into big and small animals. And so now, thinking more about these formal clusters in the data, the size axis was replaced by now a general size trend between the left and right cluster pairs. Instead of there being a global size dimension, now it's more of a discrete, the animals in the left clusters are smaller than the animals in the right clusters. She also began reorganizing the animals within the clusters a bit, and explained this reorganization with the dimensions that we show, looking at increasing furriness in a variety of different angles inside of the projection. In large part, this was the beginning of the furry attribute analysis, but then she began to look toward the fierce and the solitary attributes. She decided that the clusters on the right needed to be oriented to have similar fierce and solitary values in the center, spreading outward vertically in increasing amounts of furriness. In addition, the animals in the left cluster were now joined, and the fierce dimension was applied vertically. Finally, she added in the solitary attribute, trying to include it without disrupting the existing structure too greatly. And this was the final result of her space, now moving off of just an XY axis with a fierce dimension at a diagonal angle. So, what did we learn from this analysis process? First of all, the participant was thinking very one-dimensionally. She was approaching this one dimension at a time, trying to figure out how each of these individual attributes of the animals were affecting her space. She was also following this iterative refinement procedure, trying to introduce new information, introduce new dimensions, without disrupting these existing structures too greatly. She started off with some spatialization actions, but clusters appeared as a result of those spatialization actions. The bins that she initially created, she was hesitant to call groups. They were just an organizational construct that didn't necessarily have any meaning aside from the size of the table was limiting. But eventually, as she began to continue spatializing the data, she formed things that she was more comfortable calling groups of animals. She also generally followed this divide and conquer strategy after forming these groups. Also, when binning the attributes by size, dividing the dataset into more manageable chunks that she could perform operations on. And then finally, as you could see from that final slide, this space is very, very complex. It's not something that is easily governed by a single weight vector. Instead, there are different areas with influences of different dimensions in a variety of locations in the space. Thinking about that divide and conquer strategy for a moment, there were 3 broad organizational strategies that we saw from our participants. In the divide and conquer strategy, we started off by selecting a dimension and forming broad groups based on that dimension. After forming those groups, the participants tried to find meaning within those groups, and then after finding that meaning, merged those groups together into a final space. In the incremental layout strategy, the participant was only considering observations one at a time, and as they considered a new observation, they would add the new observation into this continually growing organizational space. And finally, in our bottom-up organizational strategy, the participant again began by selecting dimensions, but only formed small groups out of those dimensions, and eventually connected spatial relationships between those groups, forming larger and larger groups over time. With respect to structures created by the participants, we often saw that these groups were focal points in the analysis, as participants were breaking the problem down into more cognitively manageable subtasks, such as this abstract data participant who was thinking about hierarchies of clusters and cross-cutting clusters in the organizational process as she was building structures of increasing complexity, going from small pairs up to more complex overlapping groups. And finally, when we were looking at the role of domain knowledge, our labeled group participants used their external knowledge to form groups before really thoroughly investigating the data, to do structure and spatialization within those groups, and also as a confirmation check to look at the correctness of these groups and spaces. Whenever we gave the abstract data participants information about the animals, one of the common things that we saw that they would like to do was to increase the density of their groups. This is a very long, text-heavy summary of all of our study findings. To highlight some of the important ones, well, there was a very tight grouping between these grouping and spatialization actions. It was tough to decide in some cases whether a participant was grouping or spatializing. Exploring one dimension at a time was a very common thing that we saw, and participants often expressed frustration with trying to consider all dimensions at once. The axes in the projection often had meaning, and the labeled group participants were often bringing their external knowledge into these organizational structures. And finally, again, the spaces that were created were often complex, and dimensions had a varying degree of influence across the space. In particular, we noticed that local structures were more important than global structures, and participants often reported that the distances within groups were more important than distances between groups. We're interested in continuing this work, both by looking at how a participant might interpret a space that was created for them, rather than a space that they created themselves, and also, how will our results differ if our study used documents rather than using quantitative data? Thank you very much.
Hello, I'm here with John Wenskovitch. We have several questions from the chat. So the first is from Natalia, just asking, could users explicitly create axes and give labels to groups during your experiment?
Yes. Whenever we were doing this think aloud process, we wanted them to focus on the spatialization and grouping operations that they were performing and to really try to convey those. But beyond that, the results of the study were going to be very much open-ended. If a user or a participant wanted to tell us what the group's meaning was, or what the space's meaning was, we were definitely open to hearing it throughout the course of the analysis.
Great, thanks. Next question from Mikhail. Did you link your insights with how spread were those dimensions? For example, I'd rather start with a dimension that's really spread where the data doesn't touch versus almost static dimensions.
So the swims dimension in particular was one of them that the participants usually picked out on as one of the early ones to analyze. And that was very much because of the spread in the data. There was a group of animals who had a 0 in their swims attribute. And then from there, it spread out pretty widely between the 0 to 100 range. And so that's definitely one example. There are others in how they use the data distribution to decide on what their structure was going to be and what order they were approaching the dimensions, for sure.
Great. And a question from Helt. So users did not have explicit tasks beyond explore and organize the data. Follow on to that is, how would concrete tasks influence the behavior, in your opinion?
That's a really good question. I think if we gave them very concrete tasks, they would probably try to, well, I'm sure that they would try to target their exploration toward answering those questions. And so if their task was organize the space by size, or to identify what your favorite animals have in common, then their structures are very much going to be different. And so one of the big limitations of the study was we're only looking at the creation process behind these different spaces, and not so much on the analysis process. That's definitely somewhere that we want to go next, is can we present an unfamiliar projection of these animals to a participant and then try to extract their meaning. If we were to do that, then having some concrete tasks would definitely be nice, so that they could try to match a space to a task. But for the moment, that's not something that we studied.
Great. Well, thank you so much. There are a couple of more questions on Discord and in the chat, but I'm going to do my session chairly duties and keep us on time. So I'll send John over to the chat, where hopefully you can talk offline about those remaining questions. And thank you so much for a great talk. All right. So up next, we have Boba, authoring and visualizing multiverse analyses by Yang Liu and collaborators. And so if we could roll Yang's video, that would be great.
Hi everyone, I'm Yang from the University of Washington. Today I'm going to present Boba, authoring and visualizing multiverse analysis, which is a project with Alex Kale, Tim Althoff, and Jeff Heer. Over the last decade, a replication crisis has stirred many scientific disciplines. In a survey of over 1,000 researchers, a vast majority agree that there is a crisis, and most of them have experienced failures to produce results. The crisis prompts scholars to reflect on what practices might lead to false findings. A key factor is the freedom in making analytic decisions. During data analysis, one often makes many decisions, such as how to exclude outliers or what models to use. It's like wandering in the garden of forking paths, where each path might lead to different outcomes. When researchers explore multiple paths but only report the best result, they face the risk of higher false positive rates. To avoid this problem, a common recommendation is to only analyze and report one path. However, even without exploring multiple paths, many reasonable options might exist, and picking one path would be arbitrary. So prior work proposes multiverse analysis, where researchers outline all reasonable options before the analysis, execute all combinations between them, and interpret the results collectively. In doing so, the findings will be more robust to sometimes arbitrary decisions, and the report will be more transparent. Although multiverse could be a promising solution to the replication crisis, conducting a multiverse is challenging in several ways. First, authoring a multiverse is tedious because we are no longer writing a single analysis, but hundreds of forking paths. One might write one script per path, but these scripts are messy and difficult to manage. Another solution is to use nested for loops and if statements, but such deeply nested code is hard to read due to many levels of indentation. Besides authoring, interpreting the outcomes is also challenging. A typical task is to understand what decisions lead to large changes in results. Of course, the first thing to try is to use a table where cells are the results of each analysis and rows and columns map to the decisions they made. But it's difficult to tell which decisions are more influential, and it will be even more difficult if multiple decisions interact. The table is also not scalable to thousands of results. To lower these barriers, we developed Boba, an integrated system for authoring and visualizing multiverse analysis. We will use an example scenario to walk you through the Boba system. In this scenario, we will use Boba to analyze a dataset from an experiment. We want to investigate whether a modified web page layout called Reader View improves reading speed. We run the experiment, assign participants to use either the standard website or the modified layout, measure their reading speed, and collect other variables. To ensure that our conclusion is robust to analytic decisions, we identify 6 decisions in our pipeline, including choices in data processing and choices in statistical modeling. Now we are ready to write the multiverse specification. Boba provides a domain-specific language to help with authoring. With the DSL, we only need to write a shared portion of the analysis code once, and we can annotate the code to indicate decision points and alternatives. The specification is then compiled to a set of individual scripts, each corresponding to one path in the multiverse. Here is a simplifying example. First, we can write the analysis code in any programming language, such as Python or R. Then, we could insert the decision points. One way to specify decisions is placeholder variables. Boba would simply replace the variable with one of the possible values. For example, the accuracy cutoff can be either 0 or 0.6. For more complex decisions requiring multiple lines of code, we use code blocks, which divides up the code similar to cells in the Jupyter notebook. With this specification, Boba will synthesize 6 files. Here is an example output file. We can see that the placeholder variables are replaced by their possible values, and only one version of the code block model is present. In another output file, we can see that the decision of which random term to use only matters when the linear mixed effects model is chosen. For more details about the DSL, please refer to the paper. After we write the multiverse specification and execute the output files to get a collection of results, we would like to explore the results to answer our question. Does the reader view improve reading speed? How reliable is the effect? To do this, we will load the outcomes into the Boba visualizer. Here is the interface. The middle panel shows an overview distribution of point estimates from all analyses. Each dot represents an individual universe. The x-axis encodes the magnitude of the point estimates. In this case, it's the model coefficient of reader view. And the y-axis encodes count. Here we can see that the estimates fall into 2 clusters. A majority of the results are positive, but a small peak around 0 suggests no effect. What decisions lead to variations in results? To answer the question, we turn to the decision view. This graph shows decisions in the context of the analysis pipeline. It's generated automatically from the DSL specification. Each node is a decision point. Light edge encodes the order of decisions in the analysis script, and black edge encodes dependency. The color of the node represents sensitivity, so more influential decisions are highlighted in darker blues. We can see that the decision device has a large impact on results. Clicking a decision node creates a trellis plot, allowing us to further examine how results vary given a decision. Shift-clicking a second decision adds another dimension to the trellis plot. Let's go back to our most influential decision device. We can see that one condition is responsible for producing point estimates around 0. We might ask a further question. In this condition, what decisions contribute to negative results? We may brush the negative results, which updates the option ratio view, showing percentages of options in each decision as a stacked bar chart. It helps us identify options that produce specific results. Here, one type of model and two sets of fixed effects are mostly responsible for the results we just brushed. We just demonstrated how users might gauge the overall robustness of the results and explore the impacts of decisions. Besides these tasks, Boba also allows us to consider sampling uncertainty. In the outcome view, the background shape shows aggregated sampling uncertainty. We may also view the PDFs of individual universes or the CDFs. Combining uncertainty and the trellis plot allows us to compare the variance between conditions. For example, we might notice that one condition has a much larger variance than the others. Boba also enables users to consider model fit quality. We might change the color in a drop-down menu to get an overview of model fit quality. Darker color means a better model fit quality. Here, we might notice that the previous conditions supporting null effects also have a poor fit in general, implying that the results are less trustworthy. To further investigate the model quality, we might drill down to individual universes by clicking a dot. The visual predictive checks compare observed outcomes with predicted outcomes. We can see that many models give largely mismatched predictions. In contrast, here the models have much better quality as the predicted outcomes match the observed outcomes. Because we are skeptical of the results from poor-fitting models, we might use a slider to remove universes that fail to meet a quality cutoff. We call this step pruning. After an in-depth exploration, we might want to answer the final question. Given the multiverse, how reliable is the hypothesized effect? Can we conclude that the reader view improves reading speed? To do that, we go to the inference view, which should be the final step of our analysis workflow. Once here, previous views and interactions are no longer accessible to avoid multiple comparison problems from repeated inference. In the top plot, the blue shape shows the actual multiverse, and the red shape shows the null distribution where the reader view would have no effect on reading speed. The distance between the two indicates the direction of the effect. Comparing this to the spread of the density implies whether the effect is reliable. This view accounts for model quality in two possible ways. The first way is to remove the universes pruned in the previous step. The second way is to apply a weighted model averaging technique called stacking. The bottom plot shows individual universes in detail, including the point estimate and the confidence interval of the null distribution. The point estimates outside the range have an orange color. From the two inference views, we may conclude that the reader view improves reading speed, but the effect is not entirely robust. In this work, we contribute Boba, a system for authoring and visualizing multiverse analysis. We apply Boba to two multiverses from prior work. We confirm that model quality and uncertainty are potential blind spots. For example, we came across a bunch of poor-fitting models when replicating prior multiverses. While previous work emphasizes that we identify all reasonable options beforehand and report a cross-product of decisions, we found that such an approach can produce many universes with poor model fits, and many results may not provide a sound base for inferences. So we propose adding a step to the multiverse workflow where analysts must distinguish between what seems reasonable a priori versus post hoc. But should we enable more interactive ways to support these feedback loops? And if so, how do we prevent researchers from biasing the results? These questions remain future work. In summary, Multiverse is an approach for robust and transparent analysis, and Boba is a system to help you author and visualize Multiverse. Boba is open source on GitHub, and you could install the tool by a pip command. We hope that the open source tool can help more people conduct robust data analysis. With that, I would like to thank my wonderful collaborators again, and I'm happy to take questions.
Thanks for a fantastic talk. I'm here with Yang Liu, and we have a question from Remco, who asks, he's new to this notion of multiverse analysis. How does a user know all of the path they'd like to explore a priori? Doesn't that defeat the purpose of visual EDA?
That's a great question. So first of all, it does not defeat the purpose of visual EDA. It can be compatible with EDA. So first of all, the users can come up with possible alternatives from theories or methodological concerns. And then they could run a pilot study and collect the data and run EDA on the data set to check if the assumptions from the data meets their expectation and what models they can actually use to fit the data. And after that, they could run the formal experiment again to collect more data and run the entire multiverse. But when doing the multiverse, we also find that it's not really possible to plan everything a priori. Like if you do the cross product of decisions, you would run into models with poor model of equality. So that's why we think maybe we should integrate multiverse with exploratory analysis more closely. And this is an area for future work.
Great, thank you. And then I have a question from Jason Dykes. I think this will be our last question just due to time. Jason says, wonderful, but if the public can't deal with uncertainty, see yesterday's panel, what's going to happen when we tell them that we're making decisions based on analyses undertaken in multiverses?
Yeah, I agree that there's a long way to go. So right now, the intended user of our system is still people with good statistical knowledge, like the experts. But in future world, we can definitely make this more amenable to less experienced users. And also, we have prior work that do more to communicate the result of multiverse. For example, the EMARS paper from Kai 2 years ago. I highly recommend that.
Great. Well, thank you so much for a fantastic talk. If there are other questions, please feel free to continue the discussion over on Discord.
Thanks, Sheldon.
Thanks. Up next, we have supporting the problem-solving loop, designing highly interactive optimization systems. This is by Yang Liu and collaborators, and Jay will be giving today's talk. So if we could roll his video.
Hello everyone, this is Jay from Monash University, Australia. Our paper is about how to better design a highly interactive optimization system. First of all, I would like to talk about the relationship between visual analytics and interactive optimization. Visual analytics is a well-known research field which combines automatic analysis with interactions and visualization techniques to make sense of data. It is an essential tool for decision support. Another widely used tool for decision support is optimization, which is about finding the best solution to a decision problem using mathematical modeling. Interactive optimization involves users and allows them to bring their own knowledge into the solution finding process in order to find better and more realistic solutions. There are great similarities between visual analytics and interactive optimization, because both research fields aim to make the best use of humans and computers to solve complex real-world problems. Indeed, the design of visual interfaces which support people to work effectively with optimization systems can be regarded as an application of visual analytics. We have designed an interactive optimization system to solve routing problems, which schedule several trucks to pick up goods from the depot and deliver them to the customers. The aim of the problem is to minimize the total cost of all truck routes. In our system, we have provided users with different interactions to support solution exploration and analysis. For example, users can reassign customers from one truck to another via drag and drop. Users can also freeze a part of a solution and ask the system to find a new solution without making any changes to the frozen part of the solution. Here is a very short demo of our system. However, one thing that comes to our mind when designing such a system is that what design recommendations can we follow? We have looked at existing interactive optimization systems. For instance, there is an interactive visual analysis tool called Dreamlens, which is used to explore and visualize generative design. In parameter tuning, a user-guided approach is proposed to allow users to directly navigate a simulation model and change its design, while the system adjusted the underlying parameters accordingly. One more example is an interactive optimization system based on a framework named Human Guided Simple Search to solve a particular kind of routing problem. These systems have been evaluated based on the effectiveness. However, there is no attempt to develop general recommendations for the design of visualization and interactions in interactive optimization systems. Maybe we can learn something from visual analytics. There exist several models or frameworks describing high-level tasks and processes in visual analytics. In particular, Pirelli and Card introduced their sense-making loop, which captured the processes and the steps employed by analysis when analyzing and making sense of information. Similar to the sense-making loop, Liu proposed a theoretical framework called the problem-solving loop, which articulated the user goals and the tasks and interactive optimization. However, this framework was not evaluated or used for developing recommendations for interactive optimization systems. This is the motivation of our work. Now I would like to present our 9 design recommendations for interactive optimization systems based on the analysis of the problem-solving loop. The first recommendation is to provide appropriate visual representations of solutions and constraints. This recommendation is central to supporting interactive optimization because without appropriate visual representations of solutions, it is very difficult to evaluate and compare solutions. Without appropriate visual representations of constraints, it is hard to improve a solution and to adjust the underlying optimization model. The second recommendation is to support user modification of the optimization model. Being able to refine the optimization model, such as modifying existing constraints or adding new constraints, can produce more realistic and satisfying solutions. It also supports dynamic optimization if the problem changes. The third recommendation is to allow direct manipulation of solutions. Being able to manipulate and change a solution allows users to evaluate the quality of the solution in their own way. With the support of appropriate representations of solutions and constraints, users can explore the trade-offs between solutions, which is very useful for solution evaluation. The fourth recommendation is to provide a gallery of solutions. The main purpose of the gallery is allowing users to create a list of solutions based on their preferences and encouraging users to develop and evaluate alternative solutions rather than sticking to a single solution. The next recommendation is to allow user-controlled re-optimization. We think it is necessary to provide users with the ability to resolve a part of a solution. Often, users are satisfied with only some parts of a solution. Users can ask the system to improve the remaining parts of the solution using re-optimization, which makes no changes or minimizes the changes to the satisfying parts of the solution. It has the benefits of finding a better solution with a short amount of time. Also, it allows its users to explore the solutions that they are more interested in. The sixth recommendation is to support comparison of solutions. The system should allow 2 or perhaps more solutions to be viewed side by side. This allows users to identify the similarities and differences between solutions, which is useful to find the best solution. The next recommendation is to generate diverse solutions. Providing significantly different solutions, which are still of high quality, can help users better understand a problem by seeing possible trade-offs, as well as find better solutions. The eighth recommendation is to provide feedback on the solving process. Often, optimization systems give little feedback about a solving process, making it a black box. Sometimes finding a solution can take minutes or even hours or days. It would be useful to provide users with understandable feedback on what the system is doing and how long they will have to wait. The last and final recommendation is to record solution provenance. When users manipulate solutions or generate diverse solutions, presenting the provenance of each solution in terms of the steps that led to it can be beneficial for solution analysis and comparison. After presenting all 9 recommendations, one thing you might be wondering is how useful they are. We have looked at 15 representative systems from the literature. Here is what we have found. The ticket recommendations are well supported by at least a half of the exempt systems. In particular, recommendation 1 is very well supported, and it is the most commonly supported recommendation. This is expected because a suitable visual representation of a solution is fundamental to making the results of the system understandable by the end user. Whereas for the rest of the recommendations, they are poorly supported. One possible explanation is that these recommendations support higher level analysis and comparison of solutions, rather than the more obvious interactions required to construct a solution. In order to further evaluate the recommendations, we conducted a user study to do so. Specifically, we developed a tool for solving the vehicle routing problem with time windows. For this problem, as you can see that we have a home depot from which trucks pick up goods. We have a number of customers who have ordered goods. We have trucks which deliver goods to the customers. We also have 2 types of constraints associated with customers: service period and time window. Service period is the amount of time required at a customer site to deliver the goods. Time window requires that a truck has to visit a customer to deliver the goods within a certain time frame. The aim of the problem is to minimize the total cost of all truck routes without violating any service period and time window. This is an overview of our system. We have 3 main components: solution window, solution history, and solution gallery. The solution window in the middle can present either a single solution or 2 solutions side by side. The solution history at the bottom keeps track of users' interactions, such as modifying a solution. The solution gallery on the right supports user managing solutions so as to finally select the best out of many. For our study, we designed 4 different scenarios with an increasing level of difficulty. Each scenario had a certain time limit to complete a specific task. After completing the scenarios, we asked the participants to evaluate the system interface, its usability, and the recommendations. For the evaluation of recommendations, we found that most of the recommendations are of great usefulness. However, for those recommendations involving multiple solutions, they received less support from participants. One possible reason was the enforced time limit in each scenario. Most participants reported that they did not have time to work on multiple solutions and they had to continuously work on one solution because of the time limit. Therefore, more case studies are needed to further confirm the applicability of the proposed recommendations in the future. Thanks for listening.
Thanks so much for a great talk. I'm here with Yang Liu. And our first question is from Yalong Yang. Do some of the recommendations need specific supports from the optimization algorithms? For example, only optimize part of the solution. Could you please provide some insights on how generalizable your recommendations are? Thanks.
That's a good question. So the answer is yes. So for example, in order to do re-optimization, it's definitely need specific design from the algorithm perspective in order to do so. And also, generally, it's a little bit tricky in order to say provide users with different types of constraints they can add. So, for example, in our case, we allow users to add constraints such as lock the customers, as well as providing the relative order of customers to be serviced. So those things, it's actually being translated into kind of a algorithm understandable constraints from the interface perspective. And after that, being added to the optimization model itself, then the system or the optimization model actually re-optimize it in order to produce solutions based on the constraints been added by the users. So yes, needs to be specifically with the design of the algorithm itself. So the other question is for the generalizability. So that's a good question because we did the checked out the recommendations with the existing literatures, the ones that I mentioned, like 15 representative ones. So, and we realized that it has found some support of the recommendations, whereas especially for the recommendations with, say, overview of the analysis, etc., such as, say, comparison solutions, especially the last one providing solution provenance, etc. So we don't really find any good support from that aspect. And from our experiment itself, we probably have to do a bit of a more study in terms of further verifying and to test out the generalizability of the recommendations in the future. But yeah.
All right, thanks so much. We're about out of time, but if you have other questions for Jay and collaborators, please post them on Discord, and I'm sure that they'll be happy to engage. Thank you so much, Jay. So up next, we have Integrating Prior Knowledge in Mixed Initiative Social Network Clustering by Alexi Pister and collaborators. If we could roll that video, please.
Hi, my name is Alexi Pister and I will present PK Clustering, a system for integrating prior knowledge in mixed initiative social network clustering. A project with Paolo Bono, Jordan Elfeket, Catherine Plaisant, and Paola Valdivia. We worked with social scientists who analyze corpus of documents mentioning people. They study the structure of the social network in great detail and often want to cluster their data. We propose PK clustering, a new way of doing graph clustering in mixed initiative setting, which aims to give more control to the user in the analysis loop. First, users specify some prior knowledge. Then, they consolidate the expanded prior knowledge clusters with the suggestions of one or more algorithms. Finally, they can consolidate extra clusters suggested by the system. Let's look at the demo. Imagine that I am a social scientist looking for groups in the simplified version of a social network of merchants of the 17th century. PK clustering works with node link diagrams, but I will demonstrate it using VIS. All the people are listed here, and each vertical line represents a connection between two or more people. Using existing clustering tools, I would randomly choose one algorithm in a long list of mysterious names, like Louvain. I would then pick parameters I do not quite understand, run the clustering, and look at the results. But how good are those 6 clusters? Typically, I scan the names to see how it matches what I know, or what we call prior knowledge. For example, I know that Marie Boucher and Jean Masson-Lesnay are friends, so it makes sense to find them in the same cluster. However, I think that Hubert and Marguerite Antome should be together in another group. We see here that it is not the case. I might try again with another algorithm but will really prefer a more systematic method. With PK clustering, I first describe my prior knowledge by creating partial groups. I create a new group, add Marie Boucher and Jean Masson-Lesnay, and call it Group A. I then put Hubert and Marguerite Antome in another group that I call Group B, in red. When I start the clustering, all the algorithms implemented by the system are run automatically. They are ranked by how well they match my prior knowledge. The top 6 algorithms have a perfect match. Both persons of the prior knowledge group A are found in the same cluster, and the 2 persons of the second prior knowledge group B are together as well in another cluster. 2 algorithms have a partial match. Those algorithms did not match anything at all. The other people in each matched cluster are represented with these white rectangles and a number. The other clusters found by the algorithms are represented here on the right. I will start by looking at one of the most promising algorithms. I click on Ilouvin time. I see 3 groups, A, B, and others. The people from my prior knowledge are easy to spot. I can click on Others to see the other clusters in detail. But I would prefer to see how the top algorithms compare. The algorithms which gave a perfect match are selected by default. I select those 7 algorithms and click Compare. The 7 algorithms are listed on top along with the prior knowledge. By default, the first algorithm is used to group the persons. I can see that in Group B there is a lot of agreement. For many people, all 7 algorithms agree. For others, only 3. On the other hand, the consensus is less clear on the blue group. Only 2 algorithms think that Jacques Souchet should be in that group. One algorithm even put him in the red group. At this point, I will go look at the network or read other sources to decide what is best. Using the consensus slider, I can select everyone with at least 4 diamonds the same color. They appear as circles in the consolidated knowledge column on the right. I then validate the suggestions by dragging or clicking on the circles. They turn into squares and will not change again. For the other persons, depending on what I learn from the graph or other documents, I can copy the suggestion of an algorithm. For example, I believe that these people belong to the red group, along with Jacques Souchet. Or I can just leave them undecided. I am done expanding and validating the prior knowledge clusters. Now, let's look at the other clusters. Clicking on Others splits the other people by the clusters found by the currently selected algorithm. I can compare how the different algorithms do that. The clusters found are ordered by consensus. If I hover over a proposed extra cluster, shown in green now, the similar clusters found by other algorithms are shown in green. If I agree with a suggested cluster, I can validate it by clicking on its name. I then can rename it. Then, I can consolidate this new group. I repeat with other clusters, but I can leave things undecided as well. Now, I have a consensual and satisfactory partition that considered my prior knowledge. Let's review possible biases during clustering. In PK clustering, users have a lot of influence on the results and can override labels when they know the labels are wrong, based on other data they have analyzed. Our users ask to be able to do that, but it could introduce some bias as well. Moreover, if the prior knowledge is wrong, the system will try to follow the hypothesis given by the user. However, users will also see that alternative results are possible. Traditional clustering methods have issues of bias as well. Users can be primed to believe the results of the first algorithm they try, and accept results which are not necessarily good. They also often use prior knowledge to evaluate the results. Finally, they often try only a few algorithms and could miss interesting alternative clusterings. To increase transparency about how the final partition has been constructed, a summary table and reports are generated at the end of the process. For each person, we see the consolidated label along with the labels produced by the list of algorithms and what the decision was. Here is a sample of the summary table of the first case study. The rightmost column shows that the user used the Louvain time algorithm to put Eloy Antome in the Antome group. She also used the consensus of 8 algorithms to put Julien Girard in the Boucher group. Finally, she manually labeled Rose Boucher as being in the Boucher group too. The table provides a summary of the provenance of the results. It reports the size and distribution of the prior knowledge and the final partition. It then indicates statistics on how the nodes have been consolidated. Finally, it tells the number of algorithms considered and the number of algorithms selected by the user in the validation process. The summary table and the summary reports give a transparent result that the social scientist can use in her publication. PK clustering is a new approach to clustering. In a mixed initiative interactive process, it uses users' prior knowledge and proposes multiple alternative clusterings. As there is often no ground truth and several good clusterings may coexist, the user can choose the results which best fit his vision of the data. Like in any other method, biases are possible. But we believe that PK clustering provides a good balance between the advantages of algorithm power and taking users' knowledge into account. At the end, users remain responsible for reporting and justifying their choices in interventions. PK clustering is available at the following address. Thank you.
Hi, welcome back. I'm here with Alexi, and we have a question from John. When running the comparison of the algorithms, are the hyperparameters all left with default values? Would it make sense to consider the same algorithm with different hyperparameters as different options for comparison?
Yes, so basically currently in the prototype, what we do is we run so all the algorithms which have as a parameter k, the number of resulting clusters. We vary k starting from the number of prior knowledge group. So for example, if the user puts a free prior knowledge group, k will be free. And we will run also these algorithms with k plus 1 and k plus 2. And yes, so in some ensemble clustering schemes, we can vary the other parameters as well. But currently we do not do that because, for example, for continuous parameters, there will be a lot of other algorithms. So it will increase the load in the first view. But we are currently looking for some parameter space exploration to vary the other parameters as well, because it will increase the number of resulting algorithms results, yes.
Great, thank you. Our next question is from Ken. Did you consider using different clustering algorithms to investigate subclusters from the one used to find the main cluster?
I think I didn't really understand the question.
I think what he's asking is there a, did you try out using sort of a hybrid model of two clustering algorithms, one to find main clusters and then maybe a different algorithm to find subclusters? Ken, if I'm wrong, please correct me on Discord.
Yeah, no, in the current prototype, we run a bunch of algorithms existing in the literature, and then in a second step, we compare the results with the prior knowledge. So first the user enters the prior knowledge, and then the prior knowledge is matched with the algorithm's results. But it's yeah, all the algorithms are run at once, so it's kind of two separate steps. But it would be a nice lead to investigate, yes.
Great, and we have one last question for this talk that's coming from Maria. Are the relationships pairwise with no direction? And if the relationships are directional, what difference would this make? Can the same raw data be clustered according to some specified criteria?
So currently, the dataset we are working with are not directed; it's undirected graphs, and actually, it's hypergraphs. So it's people who are linked by hyper edges. So it's we mostly use datasets coming from social science. So it's documents linking several people together with hyper edges, which are the documents. And then for some clustering algorithms, we are projecting the hypergraphs into unipartite graphs, but it's not, the relationships are not directed, it's undirected and weighted graphs.
Great. Well, thank you so much. If there are other questions, please post them to Discord, and I'm sure that Alexi and collaborators will be happy to continue the conversation there. So our closing talk of this session is going to be investigating visual analysis of differently private data. This will be presented by Dan Jung, and it's in collaboration with Ali Sarvgad and Jérôme Miclau. So if we could roll that video, please.
Hello, this is Dan from UMass Amherst. Today I'm happy to present our investigation on visual analysis of differentially private data. We visualize data every day to communicate knowledge and perform exploration. However, as common applications gradually get data-driven, more and more data we deal with involve sensitive information about individuals. How should we visualize sensitive data that might involve information like people's health status or website or places they frequently visit? It is not hard to tell that direct visualization is not acceptable. Even after anonymization, attackers might still be able to identify users using site information. One might propose visualizing only aggregated data or certain statistics. Unfortunately, that's also not enough. Data reconstruction from statistics is a known and practical attack. Thus, publishing visualization of statistics might still lead to privacy breaches. We need a well-defined privacy definition to guide us through the safe visualization of sensitive data. While the preservation of privacy is a crucial goal, we don't want to go to the other extreme where we destroy or hide any useful information in the data. In data sharing or publication scenarios, we want to allow the analysis to learn knowledge about the population, like smoking rates and cancer rates are correlated in a certain state, and prevent them from learning sensitive facts like Bob has lung cancer. Among the emerging privacy protection mechanisms, differential privacy offers a provable assurance to individuals. It has become the dominant model in the research community and has been adopted by large companies like Google, Apple, and institutions like the Census Bureau. Now, I'm going to briefly describe the privacy guarantee it provides. In real-world computation involving sensitive data, the sensitive input will go through some process, producing an output. Now imagine that we have a second scenario where the user Bob opts out of the data collection, meaning that the input is exactly the same as the previous, except that the user Bob's data is removed. It then goes through the same process of computation, producing a second output. Comparing the output using neighboring input with any possible user opting out, if the difference is not larger than some parameter epsilon, we call the computation epsilon differentially private. The underlying rationale is that if anyone seeing the result of an analysis will make the same inference regardless of Bob's presence, the learned information is general data or general pattern in the data. For example, the same general conclusion that smoking can cause cancer will hold with or without Bob's data. On the other hand, if the removal of an individual leads to a different result, the output contains private information about the user. In other words, the analyst should learn very similar things whether or not an individual is in a dataset. Differentially private algorithms are usually implemented by adding well-tailored noise or resampling. Such noise injection or resampling inevitably leads to less accurate query answers and a decrease in utility or usability of output. If we take a deeper look, there is this fundamental trade-off between the level of privacy protection and the utility of the output. The privacy level is controlled by the parameter epsilon. The smaller epsilon is, the privacy requirement is more strict and really leads to more noisy output. We want to push the frontier of the trade-off to the upper right corner of the space, achieving higher utility for the same level of privacy. Epsilon is also called the privacy budget as an analogy to currency. The more you pay, the more accurate result you tend to get. And one should be careful and wise on spending the budget since it's a limited resource. Although there could be alternatives, we start with a simple pipeline where sensitive data is privatized using DP algorithms and a specific epsilon, and then fed into standard visualizers to generate private visualizations. Then, like with non-private analysis, the user performs visual analytic tasks and learn knowledge about the underlying data. So, what can go wrong in private visualizations? Let's first come back to the non-private visual analysis case. Given a visualization, the analyst performs different kinds of visual tasks to gain better knowledge about the underlying data. In order to succeed in a task with non-private visualization, the user only needs to accurately perceive the information in the plot. Here's an example. The plot shows a histogram on the marital status of people from a census data set, visualized as bar charts. Each being corresponds to the number of people that are married, single, etc. And the task is to find the marital status group with the largest count. The user succeeds if they can identify the leftmost being represent the group with the most people. However, when privacy is involved, things might change. Imagine an analyst needs to perform the same task on the same data, but this time using visualizations generated in a differentially private way. Recall that DP algorithms introduce some kind of perturbation to protect privacy. At a relatively light level of perturbation, like shown in P1, the overall pattern is still preserved, so the user will still succeed if they correctly read the figure. However, when we raise the privacy level and add more noise like shown in P2, the user will reach the wrong conclusion that the rightmost being represents the largest group. More generally, errors in private visualizations come from two sources: data perturbation error due to the requirement of privacy protection, and the perceptual error as in non-private visualizations. This leads to our first research question we want to investigate in this work. What is the relationship between epsilon, visualization type, task, and user's performance? To better understand this relationship, we conduct a crowdsourcing study following settings of prior work on the effectiveness of non-private visualizations. We recruited 176 participants on Amazon Mechanical Turk and showed them the plots in 4 different visualization types. Users are asked to perform 8 basic visualization tasks that are common building blocks for more complex analytic procedures. For example, retrieve value or find maximum extremes and anomalies. For each task, the users need to read the visualization and answer a multiple choice question. Along the process, we record users' answers and time needed to make the response. User success rates and response time are used to measure the effectiveness of visualizations. One thing to note is that since differentially private data is noisy, the accurate retrieval of value is impossible. So any answer that is within a certain range will be acceptable for retrieval tasks. Next, I'll go over our findings. First, we take a look at how noise injection perturbs the pattern and information needed for each task. The x-axis of these figures show the level of privacy protection, non-private, medium-level private, or strict private, which correspond to no noise, a small amount of noise, and a large amount of noise. The y-axis is the task success rate, capturing how well the information needed to perform a task is preserved. The higher, the better. We see two types of trends here. The performance on the highlighted task decreases slower than the others as we increase the noise level. This shows they are more tolerant to net noise injection. Based on our findings, we identified two main categories of tasks. The first category is called value task. They involve retrieving or estimating values of data points and are really sensitive to noise injection. Tasks like retrieve value, compute the route values, and determine range all fall into this category. The second type is what we call summary tasks. They tend to ask about high-level patterns in data and are usually less sensitive to noise injections. Examples include find anomalies and cluster. Prior work confirmed that some visualization types are more effective than others for performing visual tasks. With these types, users usually have higher success rates and shorter response time. Through the study, we found that bar chart and scatter plots are overall the most accurate and fastest types. Line plot is the least accurate type, and pie chart is the type that people take the longest time to respond. Our results are in line with previous studies with non-private data. Next, we found that the existence of noise influenced the perceptual accuracy or people's ability to perceive information in the plots. The influence takes effect by changing the distribution of underlying data. For a specific task, perceptual difficulties differ across data distributions. As an example, for task finding the bean with the maximum count, it will be easier for the left plot since the underlying data distribution has a single ceiling peak, while the right plot has two beans with similar counts. With the same level of privacy protection, different DP mechanisms tend to lead to noise injections of different distribution. This leads to our next research question. Is it possible to tune noise injection to improve the utility of private visualizations? First, in order to estimate the perceptual accuracy of different DP output, we define several distribution metrics that capture the difficulty to perform a visual task. Here, we're only defining metrics for summary tasks, since value tasks are perceptually less sensitive to changes in data distributions. The success of such a task mainly depends on the perturbation error or amount of noise added to the data points. For task find maximum, we define a peakedness score, measuring the extent to which there is a single ceiling peak. The anomaly score captures the degree of discrepancy between the potential outlier and the other data points. The cluster score describes the degree of existence of coherent clusters in the data. Now that we have predictive measurements for the perceptual accuracy of certain tasks, we could use them to guide algorithm choice in private visualizations. Different DP algorithms produce different output distribution based on their design. We perform a simulated comparison of the basic Laplace mechanism and two more complex algorithms that achieve state-of-the-art accuracy on answering linear counting queries. We want to see if the more complex algorithms tend to increase perceptual accuracy while maintaining low perturbation errors. Despite the complexity, some advanced algorithms tend to push the data distribution towards the harder side compared to the simple Laplace mechanisms. Those algorithms usually use techniques like grouping to help increase the accuracy of range queries, but such techniques might produce visual artifacts that harm readability. So overall, the basic Laplace mechanism is a safe choice for private visualizations, especially when the task is unknown. In conclusion, we perform a cross-all study investigating the task-based effectiveness of private visualizations. Next, we define a set of distribution metrics for perceptual difficulty and perform simulated comparison of algorithms. Based on the result, we provide insight into configuration of private visualizations. And that concludes my presentation today, and I'm happy to take questions. Thank you.
Thank you so much, Dan, for a great talk. We have time for just one question today, so I'll take a question from Nargis at UMass Amherst. A shout out to Dan and the team for investigating this contemporary and increasingly important problem. Have you thought about handling interactions for private visualizations?
Yeah, actually, that's kind of one of our ongoing work. We started with this like static setting because we believe that a lot of the, we need to kind of understand a lot of the mechanism of private visualization before being able to move on to the interactive regime. And we believe a lot of the conclusions and findings draw from the static research can be applied easily to the interactive setting. So yeah, that's a very interesting future we are currently working on it.
Great. Well, thank you so much. Attendees, if you have further questions for Dan and co, please leave them on Discord, and I'm sure they'll be happy to follow up. Thanks so much for a wonderful session today. We had 6 fantastic talks, and I hope you've all had a great viz. Jordan Crouser signing off.
We miss you, indeed. We miss you being in New Orleans. We also miss doing what New Orleanians so often do best, welcoming you to our city, telling you about our favorite places, and watching you truly experience the absolute beauty and indescribable magic of this incredibly special place. Everything that you know and love about New Orleans is not only here waiting for you, but it's better than ever. We have been busy getting ready for your arrival and have considered every detail of your visit with world-class dining, a brand new airport, new museums and attractions, and hotels to fit your every need and desire. Our world-class convention center is completing a beautiful new pedestrian park and is beginning renovations to other facilities. We'll even have gumbo on the stove, and our musicians are tuning their instruments. So when it comes time for you to return, we'll welcome you back to our table and celebrate with you our 300-year-old traditions. And we know that you will create new ones along the way.
Good morning, New Orleans. We love you, New Orleans.
Just know that we're thinking of you here in the Crescent City, and we can't wait to see you soon.
Love New Orleans. When people come, they never leave because we're swinging that way. The sun shines so bright. The breeze is so nice.
We present columnar data augmentation through visual analytics. Cava lets users augment their data with additional attributes found on knowledge graphs. To construct a new attribute, each row of a dataset is mapped to a node on a knowledge graph. Each augmented datum is the result of a query over the knowledge graph in the neighborhood of that node.
We present an efficient approach for volume and isosurface ray tracing of structured AMR data on GPU-equipped workstations, using a combination of 2 different data structures. Together, these data structures allow a ray tracing-based renderer to quickly determine which segments along the ray need to be integrated and at what frequency, while also providing quick access to all data values required for a smooth sample reconstruction kernel.
Exploring the emotions of students in classroom videos can help both teachers and parents know about students' learning status and further help teachers improve teaching. However, it is a non-trivial task to analyze the emotion evolution of a group of people from classroom videos due to three major challenges. We propose a visualization system which integrates the model uncertainty and supports both collective and individual emotion analysis.
In cancer research, it's useful to group patients based on disease spread patterns to the lymph nodes. But once we create a new clustering methodology using spatial data, how do we explain spatial clustering to non-experts? In this multi-year project, we dealt with both a participatory design stage and a broader dissemination stage, and distill specific lessons for interpreting spatial clusters.
We miss you. Indeed. We miss you being in New Orleans. We also miss doing what New Orleanians so often do best, welcoming you to our city, telling you about our favorite places, and watching you truly experience the absolute beauty and indescribable magic of this incredibly special place. Everything that you know and love about New Orleans is not only here waiting for you, but it's better than ever. We have been busy getting ready for your arrival and have considered every detail of your visit with world-class dining, a brand new airport, new museums and attractions, and hotels to fit your every need and desire. Our world-class convention center is completing a beautiful new pedestrian park and is beginning renovations to other facilities. We'll even have gumbo on the stove, and our musicians are tuning their instruments. So when it comes time for you to return, we'll welcome you back to our table and celebrate with you our 300-year-old traditions. And we know that you will create new ones along the way.
Good morning, New Orleans. We love you, New Orleans.
Just know that we're thinking of you here in the Crescent City, and we can't wait to see you soon.
Love New Orleans. When people come, they never leave, because we're swinging that way. The sun shines so, so bright. The breeze is so, so nice.